Thanks. I'm Joseph Ross, and I'm here to tell you about how we develop embedded Rust anywhere by cutting the code. So just a little bit about how we got here. I work for a company called June Life. We build modern appliances, starting with the June Intelligent Oven that you can see here. The sort of first generation of software was tied to its host platform and UI toolkit, and so it was something that was not easy to reuse on other platforms. So we set out to build a next generation of software with portability and performance and scalability and like modularity in mind. We wanted to build a suite of components that we could combine to build different appliances on different platforms, embedded platforms, very capable platforms running a full OS. And so when we started this project, we were trying to figure out what was our best choice for building portable components. First considered C or C++ as kind of obvious performant and portable choices. We have a lot of application developers on our team who come from kind of more modern languages with newer syntax like Go and Swift. And a lot of those same people had experience with C and C++ in the past and were not eager to go back to the memory management and unpredictable kind of debugging problems that often come with those languages. So we started looking at Rust. It was very new to us. This was a little over a year ago when we started looking at it. And we kind of, it looked really promising, but we weren't 100% sure that we wanted to have to kind of reinvent everything. So we had to convince ourselves and understand how to build C and C++ libraries and link them into Rust projects. Once we were confident that we could handle that piece of it, we were in. We're like, let's use Rust. This is great, and we can pull in other components when we need to. A big part of the reason why we chose Rust is it has great cross-compilation support. We can actually share parts of the code that are running on our appliances with our mobile applications to integrate with those appliances. One kind of unexpected benefit is we found that configuring building of other third-party libraries, especially for different architecture targets, was actually a lot easier to do using build.rs and just having cargo build run the whole integration of different technologies. And then as we got into focusing on embedded targets, it was really nice how much explicit control we have over how memory is getting used, whether it's statically allocated or used by the stack or the heap, and even control over like how data appears in like BSS or text sections of the binary. So the next appliance we're building is a full embedded system, so it means no standard. A lot of the support that we got from our vendors is all in C. They kind of said, what's Rust when we asked them about it. They don't support Rust. And there's a lot of members of our team who have a lot of experience building embedded systems in C. And so for our first appliance, to reduce risk, we're doing the bring up of the system in C. But we are going to, we've divided the functionality of the appliance into a bunch of different modules. And the appliance logic, so the main business logic, and the HMI and presentation implementation is all written in Rust. And then the board support, drivers and howls are written in C. Some of our, like our networking and storage implementations are also written in C. But the key thing is that we defined the different modules in the system to have these interfaces that are defined in C, but they're free of like hardware-specific types. So you can build an implementation of them using whatever technology you want. So here's kind of a little diagram of how our system is architected. The blue nodes up top are written in Rust. And we separated the appliance logic from the HMI logic because we want to be able to swap out HMI implementations for different pieces of hardware that have different inputs and outputs. The green node is kind of our API node, and so that is the header definitions that show all the function signatures defined in C that must be honored and are used by different parts of the system. This orange COM node is kind of an interesting thing. It's written all in C, and it has the network implementation, and then also some abstraction layers on top of it that provide like convenience methods that are speak more to like the logic of particular actions we're doing when interacting with the network. And then the nodes at the bottom, the how and the drivers, is largely provided by vendors, and then we enhanced it and configured it for our specific hardware. Here is a very abbreviated example of what that API layer looks like. So these are some select functions that we defined that must be implemented by some module in the system. And so we have a naming scheme where the prefix of the function describes which module will basically host that function call. So the first one, like when an incoming network message comes in, after the COM layer has processed it, it will be passed off as just the message payload to the appliance logic, so appliance on message. When the appliance wants to send information out, like a status message, it will call the COM layer and send the status out. And then a few calls for having the HMI, so like the high-level presentation logic, getting triggered with events and being able to update itself, and then the how implementation and even things like clocks. As we were building this, the key topic here is that we wanted to build a simulator for our hardware. The hardware that we're using, I have to plug in 3 USB cables to really use it completely, because there's one for power, there's one for the debugger, and then there's one for USB to UART for the console. And it's not very convenient. So we built the solution with the appliance and HMI logic as cross-platform logic, and then we rewrote any part of the system that was dependent on the hardware. We rewrote it using the simulator code, and anything where there's actual hardware sensors or hardware output, we re-implemented using widgets, like UI widgets. And since our company mostly uses Macs, we built Mac OS implementation. So it's implemented in AppKit, but there's nothing stopping you from doing it in something like Qt or even WebAssembly. And then, and as mentioned below, the device-specific networking and storage code is re-implemented in the simulator, and most of it is isolated within a submodule. So a large portion of the storage and network implementations that are on the device also run in the simulator, and it's just the hooks right at the bottom of those modules that call into either file system calls or network calls on the simulator machine versus the hardware. So back to the diagram from earlier. Once we had built these different parts, we basically dropped down a barrier between the different parts of which logic is common to any platform and which logic is hardware specific. This is where we kind of get back into this COM layer being a little bit interesting, where most of it is logic that is useful on any platform, and then there's just a few specific hooks that attach it to our hardware. And part of what happened behind that is that we actually have a Bluetooth stack implementation that works with many different architectures, including one that runs on the simulator, and that also has a different implementation on our specific hardware. This diagram kind of illustrates what I was mentioning earlier about having a swappable HMI implementation. So one of the variants of our appliance that we're working on has a screen. And so for that, we swap out with this different HMI screen implementation and use LVGL, which is a package out there with a wrapper around it, to work with that screen and then hook the LVGL implementation up to either the frame buffer on the hardware itself or a frame buffer implementation in the simulator. So some of the benefits that we experienced building the simulator is that we actually, once we had designed the different modules in the system, we were able to implement the simulator version of things faster than the board support bring up was finished. And so we were able to start building application logic and actually testing it and verifying it before the hardware was ready to use. Even once we had hardware and the bring up was all done, we had very few hardware units available, and so it made it a lot easier for many developers to work on things by not having to have hardware for all the work that was being done. We're able to, using the simulator, we're able to simulate input and output. And so we can simulate network traffic. So before we had anything that was talking to the simulator, we could basically add menu items or affordances to trigger incoming network messages and to show in a little console or text box outgoing network messages and kind of see what was happening there. So allowed us to do some early integration work. That translated almost immediately to being able to hand out the simulator to our mobile app developers, and they could develop against the simulator without having to have hardware, but it had the exact same interface, both in terms of using the UI and the network traffic. And then the simulator, because you can simulate all the inputs and outputs, we actually are able to kind of script different use cases and especially verify tricky edge cases to hardware. So one of the things we have, because our appliance is a cooking appliance, is we have a lot of temperature sensors involved. And so being able to verify edge cases around, hey, the temperature is way, way, way too high and we need to shut the system down for safety is a lot easier and safer to test on the simulator than if you actually were trying to do it with the appliance itself. Yeah. And so we experienced a lot of benefits from this, and we wanted to share it with you. We can't actually share our code as is. There's a lot of probably terrifying but also private things to there. But we built a simple version of the simulator that we would like to share with you, and my colleague Bob's going to tell you about that now.
Okay, great, thanks. Okay, so here's a kind of a smaller architectural diagram for the demo app that we put together. You may take a look at it. It's very similar to our full system. As Joe mentioned, we're using the LVGL library. It's an embedded, optimized library written in C, but we've been able to adapt that to work with Rust. Again, everything is defined interfaces at the modular level with a C-based API. So we've got kind of an example here of our driver level. This is specific to our particular board. We'll have an initialization call and then a very easy method to just turn an LED on or off or check to see if a hardware button is pushed. So we'll have an implementation for the embedded device. We'll also have an implementation on the simulator. The HMI, and that's, if you haven't heard the term before, it's a human-machine interface. It's kind of our internal term that we use for this UX layer that's higher level than your typical driver, but lower level than the application logic. So we just have a call that'll initialize its state and then periodically tell it to update in response to actions that the user has taken. And then, like I mentioned, LVGL has a very rich API that's all in C. So we've put this available on a repo, so it's there for you to check out and experiment with. On the hardware side, this was built for the STM32F429 Discovery board, pretty popular device that's got 16-bit touchscreen display, user button, and a couple LEDs. And if you get the hardware, you can run it on that. But if you don't, you can get the Mac application, build that, run it, and kind of get the experience of what it would look like running on the actual device later on. So yeah, here's kind of a screenshot. You're seeing these things in action. On the left, we've got the Mac app running in the simulator. On the right, we've got the discovery board. And since we're using exactly the same graphics library between the two, these displays should be pixel for pixel identical. And then we've got my wonderful design skills here at the bottom, 2 little boxes for the LED and a little gray box for our button. So this app is basically a simple stopwatch. Kind of the rules are push the button, you'll start the timer, the green LED will turn on, push the button again, the green LED will turn off, but the red one will turn on, the timer will stop. And then you can either push the button again to resume or do a long press and reset it. So let's take a look at this in action. So here we have it running on the simulator. Kind of see it following the different rules. And there you go. And now we can take a look at it running on the actual hardware. As you can see, the interaction is exactly the same. The LEDs are turning on and off, and the graphics screen is updating accordingly. So this was actually, pretty amazing, to see this getting exactly the same behavior on these 2 very different devices. So I want to give kind of a quick overview of the way this application was set up. It's much simpler than the actual code that we're working on, but it's more than kind of a trivial hello world example. I think there's enough substance in here that really gives kind of a flavor for some of the challenges that we had and some of the ways that we were able to solve them. So on the device side, it's basically a C application based on the little OVGL demo app, which surprisingly we removed all the graphics code from. But we use it for its kind of vendor-provided HAL functionality to bring up the board, configure the LCD display, which is actually surprisingly complicated, and run the main application loop. For the simulator, it's a Mac OS application. It's written entirely in Swift. However, the Swift compiler has this nice feature where it can import C header files and automatically build Swift bindings for them, so we can use that same C-based API. And then the simulator is just kind of hosting the UX and the shared logic. And then we have a final piece of this, which is our REST workspace. This contains all of the shared code that's used by both the simulator and the embedded device, as well as some additional platform-specific libraries. So digging down a little bit deeper into the REST workspace, we basically have 3 different kinds of crates. So libdevice, libsimulator. These are top-level crates. They actually don't have any code of their own. What they do is bring together the other common code into one place where it'll build a static library that then can be linked into the respective application. The interesting parts come in this common logic. API doesn't really have any functionality other than a bunch of C header files that the native code can read, but we'll also run bindgen on it to get automatic bindings that the REST modules can use to communicate with each other through this C API. And then to give kind of an example of integrating with a large-scale native C application, we bring in the LVGL library. There's the syscrate, which will run bindgen on it and get some extensive REST bindings, and then a higher level crate that actually wraps this kind of messy C API with a nicer, more structured Rust interface. And then we've got our HMI module, which handles the logic of trying to determine what buttons are pushed, what LEDs should turn on, and the actual graphics card. Graphics calls. One of the things that we're really excited about as the embedded Rust ecosystem matures is to just be able to move functionality that traditionally you might have done in C and actually bring it into Rust. And so we've got some examples of how that might look here. So the board crate brings together all of the kind of embedded crates, the Cortex crates, the embedded howls, puts them into one place where they're easy to manage. And then the drivers crates is actually able to use the embedded HAL APIs to define interfaces to the buttons and the LEDs. And finally, one of the really great approaches to this is it's easier to kind of debug your code on a desktop device rather than having to constantly flash it onto your hardware. So Rust already has really great integration with the LLDB and GDB debuggers, and some really solid integration with some IDEs like Visual Studio Code or CLion. We actually use both of these IDEs internally to develop our Rust code, but when you've got the simulator application, it's going to be kind of nice to sort of test this end to end. And so luckily there's a plugin that you can use that will let Xcode get some basic understanding of Rust. You can see some syntax highlighting and the ability to set breakpoints directly in the IDE. So let's kind of take a look at what that might look like. So we've got our project here. We can just run. Here we've got a simulator. I can start. I can stop it, as you saw before. Now, one of the things we demonstrated before was long pressing should reset it. Oh no, it didn't. It started it up again. Something has gone terribly wrong, so let's try to figure this out. We've got here is kind of the Rust code that is working with the display. So let's set breakpoint kind of here where we're checking for that long press. Let's stop it. The long press, release, boom. Okay, it's hit the breakpoint. It's actually brought us to the line of code. We can look down here and see that, yeah, it was about half a second that I waited to press this. Unfortunately, it didn't trigger what we wanted to. So the interesting thing when we look at it, say, okay, it's only a couple hundred milliseconds, but wait a second here. We're looking to see if the value is less than 400,000. Looks like somebody confused microseconds with milliseconds. Joe, was that you or is that me that wrote that code? Okay, so let's just pretend that that never happened. Make some changes here. Let's stop that. Rebuild our app. Just let it go. And there we go. That was the behavior we wanted. All right. So that's basically our presentation. So we found that this was a really great way to get a jump start on developing our application. It opened up the possibility of people who are more traditional web or mobile developers to start bringing their expertise into the embedded space. Made it really easy to kind of isolate bugs independent of the specific hardware, and this is giving us a really good foundation to kind of continue making more strides into bringing more and more Rust into our application as things continue to mature. And so we're planning to stick around here later today. We'll be at the Impl Days tomorrow. We brought a couple of the discovery boards, so if you want to come by and take a look at the hardware in action, we'll have it there, or feel free to check out the repo and try the Mac app yourself.
Okay, then we've got time for a few questions. Anyone have any questions for Joseph and Bob? So the question was about the hardware abstraction layer that some people in the working group and others have written for the particular board these guys are using. So I'm going to hand.
Yeah. So pull requests welcome, or if you want to take any of our code and do that with it. So to be honest, because we've been building with a different piece of hardware for a while, we hadn't really been thinking about that. But as we pulled together the sample project for this talk, we saw all these opportunities like, hey, why don't we distribute a bunch of these UI widgets that implement the HAL traits and things like that. So we're going to try to be a better community members and find opportunities to publish that, but we only just saw it.
Right, and yeah, so we're also very new to this, and so this was kind of like my first exposure, kind of seeing the HAL APIs kind of in anger. It was really kind of enlightening at the workshop days yesterday to see how much easier this makes writing the code. I've taken a look at some of the C code that our embedded engineers are working with, and yeah, it's not pretty. Compare that to these really nice abstractions that the embedded HAL has, and so yeah, we're definitely interested in seeing where we can push it forward. Unfortunately, some of the hardware that we're working with is maybe a little bit more niche because we're interested in really kind of taking advantage of like extremely low power devices and so on. So it may not be widely applicable, but there may be some opportunities for us to kind of make other people's lives a little bit easier.
The question was, can you use the oven as a reflow oven? I haven't tried it, but maybe. We do have pretty good precision control over temperatures, so there's a possibility there. And come visit us tomorrow at the Impl Days. Try out the hardware.
Yeah, catch up with them tomorrow. All right, thank you. That's Joseph and Bob, everyone.